This is lecture 14 of Machine Learning and Bayesian Inference, and today I'm going to move on from talking specifically about machine learning, and I'm going to address the last kind of chunk of this course. And this involves coming back to something that I introduced at the very beginning, which is the use of Bayesian inference in a much more general context as a means of performing inference under uncertainty. So, just to recap very briefly, last year in the artificial intelligence course I talked about the logicist approach to AI and how you can set up your knowledge about the world in a knowledge base and then infer things about the world using a theorem prover, essentially using logical inference. I then argued that approach, while entirely usable in certain contexts, experiences difficulties when you want to actually take into account the fact that the world is inherently uncertain. And at that point, using logical inference to try and implement some kind of AI system can become much more problematic. And I proposed that at present, within the wider field of artificial intelligence, the gold standard for dealing with uncertainty is probability theory, and that if you can represent the world or the bits of the world that you're interested in using a joint probability distribution, then in principle any inference that you want to make is straightforward, or an inference now becomes the computation of a conditional probability. And I also then proposed that, in fact, in practice, those computations are potentially problematic because of the computational complexity involved. Now, I'm going to start this lecture just by recapping the framework a little bit. And then I want to talk specifically about Bayesian networks, which give us a way of addressing some of the problems associated with representing the world as a joint distribution and performing inference once you've done that. I'm very briefly, going to introduce Markov random fields right at the very end, which is an alternative way of representing a probability distribution. And Bayesian networks and Markov random fields have their own pros and cons and trade-offs. But let me start by just recapping how this fits together in a very general way. The uniform way that I suggested that you could model the things you're interested about in the world when you're trying to design an agent to act in that world simply involved identifying a random variable corresponding to each thing of interest, and then writing a joint probability distribution over all those random variables. But the key underlying idea that goes with that is that those random variables are divided into three mutually exclusive but exhaustive subsets. Random variables for which you know a value are observations. Random variables for which you want to know the value are queries. And everything else is a latent variable. Aha! That should sound familiar from the last lecture. In the last lecture, we talked about latent variables in the context of unsupervised learning or clustering. And the latent variables here are of exactly the same nature. They're just things that we don't have measurements for and that we're not directly trying to infer. But latent variables may well be part of this model simply because they're involved in setting up a realistic model of the world or the environment in which our agent is trying to act. The variables on this slide are written using the usual notation. If they're uppercase, They're random variables. They could take on one of several values. Lowercase letters here are used when we have an actual observation of a random variable. Hence, the lowercase o's under point 2. Now, if we can set up a joint distribution on all those random variables, and I'm going to give an example of this in a moment, okay? It may seem a little bit odd at present because I haven't given you a specific example, but I will do. Once we've got that set up, what we want to do is be able to compute the probability distribution for our query variables, conditional on the observations that we have. So the probability of Q given O1, O2 up to OM. And in principle, this is straightforward, because if I assume for the moment that all these random variables are discrete, then we can get all the probabilities that we need from the full joint distribution just by summing things out where necessary. If any of the random variables are continuous, then that sum turns into an integral. So in principle, it's a straightforward calculation. And that's what's being shown on this slide. In the first line here, the probability of Q given the O's is something that we can get from the probability of the Q's and the latent variables given the O's just by summing out the latent variables. Okay, the usual marginalization trick. Or equivalently, I can write that in terms of the full joint distribution directly by summing the random variables corresponding to latent variables out, which is what the summation there is doing, and as usual renormalizing so that everything sums to 1. And the computation of Z is also something that we can do just by summing out the relevant random variables. I will leave you to fill in those details because I'm pretty sure I've repeated it quite a number of times by now. The other thing you can do with this picture is consider Bayes' theorem as being a means of updating your beliefs when some new information comes along. In this case, having some new information comes along just means that you get to learn an observation, a specific value, for one of the variables that was previously latent. So a new observation O prime comes along. This is an inference that you will have made before it was observed. This is the inference that is made after it's observed. And Bayes' theorem just tells you exactly how to turn one into the other. Now, I explained that in some detail in the introductory lecture, or one of the first couple of introductory lectures. And if you want more detail, I think it's easiest if I just suggest you go back and watch that again. Okay, so in principle, straightforward, but in practice, really not. Because even if your random variables are so simple that they're all Boolean, storing their full distribution, their full joint distribution, means you have to specify numbers for, 2 to the n possibilities. And n can be really big in practice. Okay, it's perfectly reasonable in a practical AI system to deal with n in thousands, for instance. That means that your storage is potentially a problem, and also that you have to establish the 2 to the n numbers that you're working with. Okay? So, establishing them in itself is potentially going to be difficult for you. How do you go about doing that? Well, of course, all this is leading up to the fact that you really can't just deal with the joint distribution in a naive way, and we'll see in a moment just how we can make this task a bit easier. And this slide was in the introductory lectures. I don't really need to repeat myself if you want me to, or hear me go through the rest of that slide again. It's already on video. So, there we are. As usual, nature gives to us with one hand and takes away with the other. Gives us this very, in principle, straightforward way of doing things. But then hammers us with the just the complexity in terms of time and memory and resources that we might need to put it into practice. So what can we do about that? Well, Bayesian networks are one way in which we can try and get a handle on these problems. They form a compact representation of the full joint probability distribution. And they are, generally, constructed either by hand, using domain knowledge for the problem of interest. Okay, that's one way of doing it, and we'll see an example of that in a moment. It is also possible, and there are more advanced algorithms for doing this, to learn the structure and the contents of a Bayesian network from examples. Okay, this is what I might put in a course in part 3 that followed on for this one, if I was going to do a part 3 course, which I'm not planning to. Bayesian networks have a specific semantics, and they lend themselves to a greater or lesser extent, depending on their structure, to the use of clever algorithms that may help us with the computational complexity problem. But before I get into detail on how to construct a Bayesian network and what you can then do with it, I want to just take a brief aside, because I need to mention the danger that is inherent in trying to treat conditional probability and implication in the same way, which is a really, really compelling thing to try and do. Okay, I think I remember myself, the early days of my study of AI, coming across conditional probability and implication and thinking, well, a conditional probability seems a bit like an implication. Unfortunately, this is not the case. They work very differently, mainly because, as you know, implication has a slightly odd-looking truth table in some senses. When you get used to it, it's completely obvious that it should have the truth table that it does. But A implies B is always true when A is false. As a result, it behaves very differently to conditional probability. But I'm getting ahead of myself. Firstly, do not fall into the mistake of thinking, as in the first bullet point here, that if you've established that the probability of x conditional on y is 0.1, you can't conclude that if you know the value of y, then the probability of x is 0.1. This is not a good thing to do. The thing is that the probability of x expressed on its own is a prior probability, meaning that it's the probability you assign to x when you have no evidence whatsoever. Okay? If you talk about the probability of x conditional on y, that's appropriate when y is all of the evidence that you have. And its value may change if new evidence comes along. So the probability of x conditional on y and z may be completely different. Okay, so if you happen to know the value of y and you have established that the probability of x conditional on y is known, you can't just use that known value as the probability of x if you happen to know the value of y. Okay, it's a more complicated quantity than that. Now, where its comparison with logical implication is concerned, the easiest way to visualize this is if you look at these things in terms of Venn diagrams. On the left, well, we know that the probability of A implies B could be interpreted as the probability of not A or B. A and B are marked here as sets representing events in precisely the same way as you might represent them in a first course on probability. And on the left, shaded, is the area of probability corresponding to the probability that A implies B. On the right, well, we know that the probability of A conditional on B is the probability of the conjunction divided by the probability of B. Okay, and the lightly shaded area on the right is the probability of the conjunction, and the full extent of the shading, the light and the dark, gives us the probability of B. We can see that these are very different things. Okay. Now, if you want to sort of think this through a little bit, imagine that fish are very rare and most fish can swim. With implication, you've got the probability that a fish can't swim is the probability that something's not a fish or it can't swim. And if fish are very rare, then the collection of things that aren't a fish is going to be big, and your probability will be your probability as a consequence will be big as well. If you look at conditional probability, you then have the probability that something's a fish and it can't swim divided by the probability that something's a fish. And if most fish can swim, that's going to be a small probability. So here we have a really direct illustration of how these two concepts differ. And this is disappointing. It would be very, very nice if I could come up with a logic that incorporated probabilities and implication in a sensible way. And there's a lot of interest in trying to do this. But it's tricky, and this is part of the reason that it's tricky. Anyway, let us get back to the main point. Now, the key idea here is that we can use the idea of statistical independence to try and impose structure on the joint distribution that we make using a Bayesian network. Okay? Independence, or more specifically the idea of conditional independence, which is slightly different and something that you're probably less familiar with. These together allow us to construct Bayesian networks that embody the structure of the random variables within the problem of interest. Okay, now, once again, for the purposes of this course, a Bayesian network is going to be made using domain knowledge. Okay, by looking at the domain of interest, one may be able to infer that there are conditional independences involving random variables, and the existence of those conditional independences constitutes structure that we might be able to exploit. Now, to use a very simple example, I have here an incredibly simple world involving a coin flip and the roll of a die. If I flip a coin and roll the die, I will get an outcome, say a head and a 2. And to a rough approximation, I'm going to need 12 numbers in order to describe this small world. The numbers here correspond to what happens if the probability of a head is 0.3 and the die has a probability I over 21 for its ith outcome. Okay, so these are highly biased, but I can write down a full joint distribution. Okay, I have a bunch of numbers here. They cover all the possible outcomes, and they are positive, or they are non-negative, and they sum to 1. Okay, that's a joint probability distribution. Now, that's 12 numbers. Now, of course, I could get away with 11, because I know that the last one must be 1 minus the sum of the others. But that's only ever going to get us a little bit of an improvement in terms of how many numbers we have to specify. Now, hopefully, you will immediately see how the fact that the coin and the die are independent of one another can simplify this a little bit. Okay, so we know that the joint probability here is the product of the individual probabilities for the coin and the die, because the coin and the die are independent of one another. Now the coin, we need two numbers to specify, probability of head, probability of tail, and the die we need 6, so we actually only need 8 numbers there. Okay. We got 12 numbers down to 8 by exploiting an assumption regarding independence. Now that's all very nice, but in practice it's not necessarily the case that we can actually assume that random variables are fully independent of one another. We need kind of a halfway house between these. And that's something that comes from the idea of conditional independence. So let's look at something slightly more complicated. Here I've got, again, a very small world involving initially 3 random variables: heart disease, chest pain, and shortness of breath. And what you see at the top is a joint distribution covering the possibilities for those random variables. Okay, and we need 8 numbers to specify it, because each of these random variables is Boolean. Now I'm then going to add a 4th random variable, which is one with 3 values, corresponding to the outcome of the Oxford versus Cambridge Tiddlywinks competition. This outcome can be Oxford, Cambridge, or a draw. Now, 4 random variables: heart disease, chest pain, shortness of breath, Tiddlywinks competition. We want a joint distribution on these. Well, initially we can play the same trick, because the outcome of the Tiddlywinks competition is statistically independent of any particular person's cardiac health. Now, of course, we can split hairs here and say if someone is extremely keen on the outcome of the Tiddlywinks competition because, for example, they bet £10,000 on a particular outcome, then if they have a bad heart, these things may be connected in some way. But we're not going to do that, okay? We're just going to assume that these are in fact independent of one another. Now, we can split in the usual way, and this is going to be done a little bit more generally in a moment, a joint distribution into a conditional distribution and a prior. Okay, probability of A given B is probability of A and B is probability of A given B times the probability of B. Okay, B here is just the collection, the conjunction of HD, SB, and CP. But we can assume that the outcome of the Tiddlywinks competition is independent of the other 3 random variables, and one way of defining independence is like this. Okay. So we can get from 24 down to 11 numbers to specify the full joint distribution. As previously, if we'd actually taken the naive approach, we'd have 3 Boolean random variables and 1 with 3 values, so we'd need 2 times 2 times 2 times 3 numbers to fill in the table. Now we've split it, we need 8 to fill in the table for HD, SB, and CP, and we need 3 for the outcome of the Tiddlywinks competition. Okay, so from 24 down to 11. But we can do something a little bit cleverer still. Now here is the really sort of key definition. And at this point, I'll say that this is the definition that you really do get to play with in designing a Bayesian network. And it also is tied up with the idea of a Bayesian network in a way that maps very nicely onto the idea of causality. Okay, that the outcome of a random variable has a direct effect, in some sense, on the outcome of another. Okay, this is a very good and common and general and usable abstraction in modelling things within the world in practice. You change one thing, it has an effect somewhere else. Maybe several different places. And conditional independence and Bayes nets embody that idea very naturally, as we'll see in a moment. Now, here's the interesting thing with these remaining three random variables. They are not statistically independent. But you can think, really, of the heart disease part as directly causing the chest pain and the shortness of breath. Okay? In probabilistic terms, this leads to the chest pain and the shortness of breath being conditionally independent given heart disease. And it means that we can write this. Okay, this is the key idea. And in the shaded box we have the general definition. Okay, A is conditionally independent of B given C if the probability of A and B given C is the probability of A given C times the probability of B given C. Or, as an equivalent, and you should prove that these two are equivalent, it's straightforward manipulation of probabilities, it's, but it's worth doing. Equivalently, A is conditionally independent of B given C if this holds. Okay. So the probability of A given that you know B and C is just the probability that you know A given C. Okay. The presence of B there doesn't really change anything for you, so you can just drop it. And I think I find that one easier to justify in my head. Okay. I think that the probability of chest pain given shortness of breath and heart disease is just the probability of chest pain given heart disease, because the heart disease directly causes the chest pain. Okay? The shortness of breath does not. Now again, you might argue somewhat with this conclusion. The interactions between these three random variables may indeed be such that they're not quite conditionally independent in this way. But as is always the case, when you set up one of these to model the scenario that you're interested in, there will be a trade-off in the complexity of what you end up with, in the sense that the computational complexity of dealing with your final Bayesian network may be considerably increased if it more accurately reflects reality. Okay? But if you're willing to make stronger assumptions about conditional independence, then you may find that the computational complexity of dealing with your resulting Bayes net is reduced, and there is a trade-off between the level of fidelity that you want in your model of the world and how much complexity in terms of making computations you're willing to deal with. Okay, but this is the key idea: conditional independence. And conditional independence tends to be something that is much more defensible as an assumption in modelling things in the world than full-blown statistical independence. Okay, it's something that you generally can say something about. And once again, that's because it essentially corresponds very well with causal relationships. Okay? The heart disease causes both the chest pain and the shortness of breath. Okay, and that gives us this conditional independence assumption. So that means that this kind of relationship can be inferred. Okay, but let's look at this with a concrete example. After a regrettable incident involving an inflatable gorilla, a famous college has decided to install an alarm for the detection of roof climbers. The alarm is very good at detecting climbers, but unfortunately It's also sometimes triggered when one of the extremely fat geese that lives in the college lands on the roof. One porter's lodge is located near to the alarm, and the porter inside that lodge has excellent hearing and a pathological hatred of roof climbers. And he will always report an alarm, and in fact his hearing is so good, he sometimes thinks he hears an alarm, even when there isn't one. In the other porter's lodge, which is a considerable distance away, there is an older chap with dodgy hearing who likes to listen to death metal very loud. And so he is less likely to end up making a report when an alarm occurs. Now we want to represent this little piece of the world using a Bayesian network. So here we have one. Notice we have immediately some causal relationships. The climber can influence whether the alarm is sounded, and a goose can influence whether the alarm is sounded. But climbers and geese don't influence one another. Okay? Goose don't follow the climbers, climbers don't follow the geese. Okay? So there is some independence that can be assumed between climbers and geese. We have initial probabilities for there being a climber or a goose on the roof. 0.05 for the presence of a climber and 0.2 for the presence of a goose. We then have an alarm, which is influenced by both climbers and geese. And as you can see, it is very likely indeed to go off if both a climber and a goose are present. Slightly less likely to go off if it's just a climber, but still good at detecting them. And rather less likely to sound if there's just a goose or if there's nothing at all. And finally, the alarm can affect whether or not each of the porters' lodges raises a complaint. The alarm could cause either porter's lodge to raise a complaint. In the case of Lodge 1, there's a very high probability that a complaint will be raised if the alarm is going off, and in the case of Lodge 2, it's rather less. And Lodge 1 and Lodge 2 don't directly influence one another. Okay? Lodge 1 doesn't phone up Lodge 2 and say, "Hey, did you hear something?" Okay, so we have a kind of natural causal relationship here, and we have some probabilities telling us how these random variables act. Okay? And that's a Bayesian network. What we need to do now is say something about what it actually means. So, just to recap and to be a bit more specific, a Bayesian network has a random variable at each node. It's a directed acyclic graph. Each node has a probability distribution conditional on its parents. And roughly speaking, if you've got an arrow from one node to another, it represents the presence of some kind of direct influence. Now, what follows then is the question of what exactly we can infer if we construct a Bayesian network in this way about the conditional independences that it embodies. And this is a little bit more complicated than you might expect. But I think it's safe to say that the real emphasis should be on the causal relationship. And that's the thing to really bear in mind when looking at or designing one of these things. What we're just going to see here is that you can ask, in general, what conditional independence assumptions a particular Bayesian network imposes on its variables. So the first thing we have to define is how exactly one constructs a full joint distribution based on a specified Bayesian network. Now, at the moment, all my random variables are still discrete. In fact, in this example, they're all Boolean, and that means you can represent them with a table of numbers. I'm going to talk a little bit later in the next lecture about what happens if any of them are continuous. Okay, but we're just going to continue with the discrete assumption for now. The climber and the goose only have prior probabilities. You're going to have some of those because this is a directed acyclic graph. Okay, some things won't have parents. And the key idea is that the full joint distribution that's represented by a Bayesian network is just the product of these priors and these conditional distributions, one for each node. Okay, so this is saying that if you have a Bayesian network with small n nodes in it, okay, small n random variables, the probability of any particular combination of values is the product over each node of the value given by the conditional distribution for the corresponding variable. Okay, and if it's a prior, so it has no parents, then we're just using the prior probability there. Now, the example at the end of this slide is just a simple example showing that the probability that there's no climber, no goose, the alarm sounds, and both L1 and L2 kick up a fuss, is the probability of, is the product of the probabilities for each of those individual nodes read off from the totals associated with the diagram. Okay, so the first thing in here is the probability of L1 given A, okay, which is read off from here, and the probability of L2 given A read off from here, and so on. Okay, so the mapping to a full joint distribution over the random variables is easy. What can we say then? Well, as a general rule, we know that we can split full joint distributions into conditional distributions. Okay, and the idea with that is that because we know that the probability of A and B is the probability of A given B times the probability of B, if we've got a whole bunch of random variables, as in the second line, we can start by splitting like this. Okay, probability of one of those random variables conditional on all the others. Okay, so there's a bunch of orderings in which you can do this this process. Okay, so one of them conditional on the others times the probability of the others, and now the probability of the others is just a joint distribution, so we can repeat this. Okay, so what that means is that I've got the probability of one of them conditional on the others, and then I get to pick one from the others. I have the probability of that one conditional on everything that's left, and so on, all the way down to the probability of just a single variable. Okay. Or if you want to see it, just for a minimal kind of example, you could write the probability of A, B, and C is the probability of A given B and C times the probability of B given C times the probability of C. Or you could do that in any order you like. Okay, you could say that it's the probability of B given A and C times the probability of C given A times the probability of A. Yeah, there's a bunch of orderings in which you can do it. But the key point here is that if you compare this with what we had on the previous slide, namely this, what you can see is that a Bayesian network makes the assumption that each node, or the random variable for each node, is conditionally independent of its predecessors given its parents. Okay, now that's one of the things that you can infer from this way of representing a joint distribution, but there are others which I'm going to come on to in a moment. However, that is a good place to stop now. So what are the take-home messages for this lecture? Well, first is that for reasoning under uncertainty, we can replace a logical database and logical inference with a joint probability distribution and the computation of conditional probability. That computation is in principle straightforward, but in practice, if you're going to deal with any kind of naive representation of the full joint distribution, it's likely to be problematic for you. So we need a non-naive representation of the full joint probability distribution. And a Bayesian network gives us that because it allows us to impose structure on those random variables to a first approximation by thinking about causal effects between them. Having done that, we can use smaller probability tables and combine them to get a full joint distribution. That means we have less in terms of the numbers that we have to come up with. It also means that if we've been sensible in terms of how we've done this, we can probably use domain knowledge not only to come up with the structure of the network, but to come up with the numbers to put in these tables. Once we've done that, we have a simple way in which that Bayesian network maps onto a full joint distribution over all of its random variables. And it expresses particular kinds of conditional independence between random variables that in practice are things that we can generally assume when dealing with a specific world or environment that we're trying to model. Okay, so in the next lecture I'll continue with this. I'll say a bit more about what conditional independences a Bayesian network can be said to express, and I'll look at how this might help us, how all of this might help us to do inference more efficiently when we want to try and start with a Bayesian network and extract a conditional probability from it.